Hello and welcome back to Mech Zone. In the previous lectures, we have studied about heat transfer taking place by means of conduction and by means of radiation. We also studied about the heat exchangers, the classification of heat exchangers, LMTD, NTU, and all the related phenomena. Now, this is the last series of the lectures in case of heat transfer subject, and today we will be studying the topic of convection. Now I have already explained to you about the basics of convection in the previous lectures. You can look for the lectures of 1, 2 and 3, basics of heat transfer, where I have explained all the basic theories of conduction, convection and radiation. Now I will directly start with the topic convection. आप अगर मेरा कोई भी लेक्चर देखेंगे तो उसमें आप एक चीज़ ये ऑब्जर्व करेंगे कि मैंने सिर्फ और सिर्फ उतना ही मटेरियल आपको प्रोवाइड कराया है जितना आपको प्रॉब्लम सॉल्व करने में और आपको एग्जाम अच्छे से क्रैक करने में हेल्प करेगा. आई हैव नॉट unnecessarily introduced any material जिसको आपको पढ़ के बहुत ज़्यादा बोरिंग फील हो या बहुत ज़्यादा हेडेक हो, क्योंकि कम से कम मटेरियल रखना और उसे इफेक्टिवली याद कर पाना इज़ अ बिग चैलेंज इन गेट, बिकॉज गेट इज़ अबाउट 100 मार्क्स और 100 मार्क्स में से अगर आपके 80 मार्क्स नहीं आते हैं देन PSU का सपना थोड़ा मुश्किल हो जाता है. सो टुडे वी विल स्टार्ट विद द टॉपिक ऑफ कन्वेक्शन. नाउ द actual meaning of convection is going away. The actual meaning of convection is going away. Now we already studied that in case of convection Q is equals to HA delta T, where A is what? A was the convection area. A was the convection area. Delta T was the temperature difference, and H was the convective heat transfer coefficient. Convective heat transfer coefficient. Convective heat transfer coefficient. Now we will see the Newton's law of cooling that we have discussed, that Q is equals to HA Ts minus T infinity, where Ts is the temperature of the surface and T infinity is always the temperature of ambient surrounding. Ambient is the temperature of the ambient surrounding. Now actually convection is divided into two major portions and we will separately study these portions. The first one is called as forced convection. First one is called as forced convection, and the second one is called as free convection. Second one is called as free convection. So we have forced convection and we have free convection. In case of forced convection, velocity is evident. Velocity is evident. And in case of free convection, there is no velocity evident. There is no requirement of velocity. Okay, and here the flow is naturally occurring. Flow is naturally occurring due to buoyancy forces arising out of density differences, arising out of the density differences or density changes of fluids. Okay, now in case of the forced convection we will study two main cases, that is, first one is flow over flat plates. Flow over flat plates. The second one would be flow through pipes or ducts. Flow through pipes or ducts. Now here we will see that if this is a flat plate such that there will be a formation of HBL. HBL stands for hydrodynamic boundary layer, and the velocity profile would be like this. This is the x direction, this is the y direction, this is V infinity. V infinity means velocity of the ambient fluid. So here there will be a formation of hydrodynamic boundary layer. In case of flow through pipes or ducts, we will have this type of variation. We will have this type of variation in case of velocity, and we will see that velocity is maximum at the midpoint or through the midline of this pipe. Okay, now this is actually the distribution of velocity in the pipe, and here we have the radial distance r, where r is actually the radial coordinate. It is the radial coordinate. It is the radial coordinate. For example, if we consider a hot vertical plate such that the temperature of the plate is quite high, then the movement of the air or the fluid around this plate would be in this upward direction. Why it is moving upward? Because the density is decreasing as the temperature is increased. Now, why the density is decreasing? It is because on gaining heat or on increasing the temperature, the molecules get energized, as a result of which the vibrations amongst the molecules starts increasing and they start to vibrate vigorously, as a result of which the distance between the molecules keep on gets increased. So when the distance between these molecules is increased, the volume gets increased, and when the volume is increased, the density gets decreased. Okay, now in case of the hot sphere, we will have the flow pattern like this will be the flow pattern in case of the hot sphere. Okay, now we will start with forced convection heat transfer. We will start with forced convection heat transfer. Forced convection heat transfer, and we will find that the convective heat transfer coefficient in case of forced convection heat transfer is a function of V bar. V bar means the average or the mean velocity, D is the characteristic dimension, rho is the density, mu is, you already know what is mu, Cp heat capacity, and K is the thermal conductivity. Okay, now if we consider rho, mu, Cp and K, these are the thermophysical parameters. These are the thermophysical parameters. These are the thermophysical parameters, where D is the characteristic dimension of the body, or the dimension which is to be used for the calculation of dimensionless numbers. Okay, solid properties do not influence H. Solid properties are not going to influence H. Okay, now if we apply the Buckingham pi theorem of dimensional analysis, and we will solve for our equation, and I need not to derive all those expressions for finding out the degree to which these individual and specific parameters will be raised to, and we are not going to find out the dimension, but I am directly writing one result that will be obtained from the Buckingham pi theorem, that Reynolds number which will be obtained, it is equals to rho Vd upon mu. It is rho Vd upon mu, where rho is the density, V is the velocity, D is the characteristic dimension, and mu is the viscosity. Okay, this will be obtained from the Buckingham pi theorem analysis. Okay, so one dimensionless number that was obtained by the Buckingham pi theorem analysis, it was Reynolds number, and Reynolds number came out to be rho Vd upon mu. Another dimensionless number that will be obtained from the Buckingham pi analysis is Nusselt number, that would be equals to Hd upon K. Now I already explained to you when I was explaining Biot number. Here also the formula is Hd upon K, and there we had the formulas as HL upon K. Here K is for the liquid, and in the Biot number it was for the solid. So these 1 mark questions can also be asked in the interviews. The next dimensionless number that we will obtain in the forced convection analysis, that is Prandtl number, and Prandtl number is equals to mu Cp upon K, and we will find that for the forced convection heat transfer, Nusselt number is actually a function of Reynolds number and Prandtl number. Please remember this, that for the forced convection, Nusselt number is actually a function of Reynolds number and Prandtl number. Now if we look at Reynolds number, we know that kinematic viscosity is equals to dynamic viscosity upon density. So rearranging the terms, we can write Re is equals to Vd upon nu. Vd upon nu. Now since the velocity is coming in the numerator, we can write that the top or the numerator signifies inertia forces, and the bottom is corresponding to viscosity, so it is viscous forces. This question has also been asked in GATE, but it was asked in the way that the ratio of the inertia forces to the viscous forces will be called as, and the answer is Reynolds number. So GATE asks very simple questions, but you have to be very thorough with the data. Okay, you have to be very thorough with the data. Now what does nu signifies? Nu is the kinematic viscosity. It signifies the momentum diffusion. This is very important. Momentum diffusion rate. That at what rate the momentum is being diffused from one layer to the other, or it is also called as momentum diffusivity. It is also called as momentum diffusivity. This is also called as momentum diffusivity. Okay, now say we have two flat plates, and these flat plates are kept one above the other such that in between these flat plates we have the flow of a fluid. The bottom plate is fixed such that its velocity becomes 0, and the top plate is being pulled by a force P, which is constant in nature. Now the upward direction is the y direction. Since this plate is fixed, the layer of the fluid which is just in contact with this plate will be at rest because of the no slip condition. There will be a no slip condition due to the viscous nature of the fluid which is flowing in between these plates, and we will see that there is a development of velocity profile. This will be the velocity profile on going upwards, such that del u over del y will be the velocity gradient. This will be the velocity gradient, okay, between the two plates, such that velocity will be a function of y. And we see that at this point the velocity is 0, and velocity is gradually increasing such that the slope is also increasing. Slope is maximum at this point and becomes 0 at the top. So slope is gradually decreasing as we move upwards, whereas velocity is increasing. Okay, now one very important point here, we will discuss about Newton's law of viscosity. Newton's law of viscosity. Now according to the Newton's law of viscosity, tau is directly proportional to du over dy, that is the shear stress is directly proportional to the velocity gradient. Now when this proportionality sign is removed, there will be a constant and it will be introduced here, that is tau is equals to mu du over dy. Tau is equals to mu du over dy. Okay, so this will be the Newton's law of viscosity, that is we can write in words viscous shear is directly proportional to the rate of shear strain. It will be directly proportional to the rate of shear strain. Now this viscous shear is actually non-conservative in nature. And we see that mu of the air, this data is generally given at room temperature. If we talk about at room temperature, it is nearly about 18 into 10 to the power minus 6 Pascal second. Okay, the kinematic viscosity of air at the room temperature is about 18 into 10 to the power minus 6 Pascal second. And if we find out the Reynolds number, and if its Reynolds number is less than 2000, it signifies flow is laminar. If Reynolds number lies between 2000 and 4000, the flow is transition flow. And if the Reynolds number is greater than 4000, then the flow becomes turbulent. This laminar flow is also called as viscous flow. Now, in case of the laminar flow, if we look through a pipe, if in a case of a laminar flow, the fluid particles will be moving all in a same straight line without any haphazard or zigzag motion. This is the characteristics of laminar flow. लैमिनार फ्लो को हम अपने घर में भी ऑब्जर्व कर सकते हैं. जैसे हम लोग नल को अगर बहुत ही धीरे खोले तो आपने देखा होगा एक बहुत स्मूथ सी जो धार है वो नल से गिरती है. तो वही जो एकदम स्मूथ धार है, दैट इज कॉल्ड एज द लैमिनार लो एंड इन लैमिनार फ्लो. एंड इन केस ऑफ द लैमिनार फ्लो देयर इज नो इंटरमिक्सिंग ऑफ द फ्लूइड पार्टिकल्स. देयर इज नो intermixing of layers of the fluid. There is no intermixing of the layers of the fluid. Okay, now on the other hand, if we see the turbulent flow, then it will be very haphazard in nature. इसमें क्या होगा? Now here we have, if we look in the laminar flow, in case of the laminar flow, the velocity distribution is parabolic in nature. Please remember this data, that velocity distribution is parabolic in nature in case of laminar flow. Whereas if we talk about this turbulent flow, then the velocity profile becomes more flatter and it will be a logarithmic nature of profile for velocity. Logarithmic nature for the velocity profile, such that there will be mass intermixing of the fluid particles between these layers, and chunks of fluid particles will jump from one layer and they will enter the other layers. That is, in case of the turbulent flow, this is for the turbulent flow, the value of H, that is the convective heat transfer coefficient, is generally high, and the value of H, that is the convective heat transfer coefficient for the laminar flow, is generally low. Please remember this, that value of H for turbulent flow is large as compared to the value of H for laminar flow. And we will see that क्योंकि H की वैल्यू फ्लो के टर्बुलेंट होने से बढ़ रही, तो हम ये भी तो कह सकते हैं कि रेनॉल्ड्स नंबर के बढ़ने से, अगर रेनॉल्ड्स नंबर बढ़ेगा तो हमारा फ्लो ज़्यादा से ज़्यादा टर्बुलेंट साइड पर जाएगा, और रेनॉल्ड्स नंबर के बढ़ने से ही हमारे H की वैल्यू भी बढ़ती है. तो ये भी डेटा हम याद रख सकते हैं कि रेनॉल्ड्स नंबर को अगर हम इंक्रीज करेंगे तो कन्वेक्टिव हीट ट्रांसफर कोफिशिएंट की भी वैल्यू हमारी इंक्रीज करेगी. नाउ वी विल डिस्कस द फ्लो ओवर फ्लैट प्लेट्स. फॉर एग्जाम्पल, इफ दिस इज अ फ्लैट प्लेट, okay, and the hydrodynamic boundary layer is being formed like this, such that this is the y direction and this is the x direction. This is the side where we have V infinity, that is velocity of the ambient fluid is flowing. This side or this edge will be called as the leading edge. This edge is called as the leading edge, and this edge is called as the trailing edge. This edge is called as the leading edge, this is called as the trailing edge. Now the layer of the fluid which is just in contact with this plate, I'm making it with red color. The layer of the fluid which is just in contact with this plate, this will be the stagnant layer. This will be the stagnant layer. This will be the stagnant layer of the fluid. Okay, now we will see that the velocity profile is like this. The velocity profile is like this. This thickness is called as delta, that is hydrodynamic boundary layer thickness. Delta is the hydrodynamic boundary layer thickness. How thick is the boundary? And this is the velocity profile. We see that at this point the velocity is 0 and the velocity is increasing as we move upwards, but del u upon del y is actually the slope of the velocity and it is decreasing. Here it is maximum at this point, then it is gradually decreasing, decreases as we go up, decreases as we go up, and v infinity is actually called as the free stream velocity. Free stream velocity, it is called as the free stream velocity. Now if we see the case of an aerofoil, this is the aerofoil now, and if the fluid is flowing like this, then the distribution will be like this. This is actually the hydrodynamic boundary layer. Now in case of a cylinder, if we look at, the flow will be like this. This is flow across a cylinder. Okay, now viscosity is the main or the prime reason for the formation of hydrodynamic boundary layer. Please note that viscosity of the fluid is the main reason for the formation of hydrodynamic boundary layer. This viscosity, actually what it is doing, if one layer is moving over the other layer, so the viscosity or the viscous shear is trying to retard the motion of one layer which is moving over the other. कोई भी एक लेयर है वो दूसरी लेयर के ऊपर स्लाइड कर रही है. अब ये वाली जो लेयर है ये आगे जाना चाहती है, बट न्यूटन्स थर्ड लॉ, दैट इज एवरी एक्शन हैज इक्वल एंड अपोजिट रिएक्शन के कारण ये वाली जो लेयर है नीचे वाली, ये इसको पीछे धकेलना चाहेगी. तो ये आपस में इन दोनों में एक विस्कोसिटी या फिर एक रेजिस्टेंस डेवलप होगा. उसी रेजिस्टेंस को हम लोग कहते हैं विस्कोसिटी, और विस्कोसिटी इज द प्राइम रीजन फॉर द फॉर्मेशन ऑफ हाइड्रोडायनेमिक बाउंड्री लेयर. Now hydrodynamic boundary layer thickness, it is called as delta, and it is actually a function of x. It is actually a function of the x coordinate. Okay, now within the hydrodynamic boundary layer, velocity gradients exist. But if you look at outside the boundary, then there will be no velocity gradients. There will be no velocity gradient, and outside this boundary, everywhere the velocity will be equal to v infinity. Now since du over dy is existing only within the region of hydrodynamic boundary, we can say that here we will have tau is equals to mu du over dy. There will be shear stress definitely, and if there is shear stress, then here the flow will be irrotational flow. If means here the flow will be rotational, because now it will create a rotation of the fluid particles. Here the rotation of the fluid particles will take place, and outside the hydrodynamic boundary layer du over dy is 0, hence tau is 0, hence we will have irrotational flow outside the hydrodynamic boundary layer and rotational flow within the hydrodynamic boundary layer. Actually this I will again teach in the fluid mechanics subject, but since it is here, so I am discussing it with you all. Now if I wish to obtain Rex, x stands for local Reynolds number, that would be v infinity x upon mu. V infinity means infinity of the fluid that is flowing, x means at that particular location of x, or it can also be written as va infinity x rho upon mu, that is mu is equals to mu upon rho. This is called as new, new, it is called as new. Okay, if we talk about flat plates, for flat plates Reynolds number x, that is a local Reynolds number, should be less than 5 into 10 to the power 5 in order to have the flow as laminar. जो हमने प्रीवियसली डिस्कस किया था कि रेनॉल्ड्स नंबर लेस देन 2000 होना चाहिए, वो एक्चुअली हमारा किसके केस में था, पाइप्स के केस में था और डक्ट्स के केस में था. बट अगर फ्लैट प्लेट्स की बात करें तो रेनॉल्ड्स नंबर अगर 5 इंटू 10 टू द पावर 5 से छोटा है तो हमारा फ्लो लैमिनार होगा, और अगर हमारा 5 इंटू 10 टू द पावर 5 से बड़ा हो गया देन फ्लो विल बिकम टर्बुलेंट. ओके, बट अगर हम कॉमनली ऑब्जर्व करें और प्रैक्टिकल एप्लीकेशंस की बात करें तो प्रैक्टिकल एप्लीकेशंस में हमारा जो भी हीट ट्रांसफर होगा वो लैमिनार फ्लो ही होगा ओवर फ्लैट प्लेट्स. ठीक है, और टर्बुलेंट फ्लो कहाँ होगा, हमारा पाइप्स एंड डक्ट्स में होता है. जनरली पाइप्स एंड डक्ट्स में हमारा टर्बुलेंट फ्लो होगा, वेयरएज लैमिनार फ्लो हमारा कहाँ होगा, फ्लो ओवर फ्लैट प्लेट्स में. ओके, अगर इसी की डायग्राम की हम लोग बाउंड्री कंडीशंस को देखें, ध्यान से बाउंड्री कंडीशंस को देखें तो क्या देख सकते हैं, y जहां पर 0 है, यहां पर भी y 0 है, यहां पर भी y 0 है, वहां पर u भी क्या हो गया, 0. वेलोसिटी इज ऑल्सो 0. दिस इज वेरी इंपॉर्टेंट बाउंड्री कंडीशंस. ओके, सो जहां पर हमारा y कोऑर्डिनेट 0 है वहां पर हमारा वेलोसिटी भी क्या हो गई, 0 हो गई. जहां पर y इज इक्वल्स टू डेल्टा है, मतलब बाउंड्री लेयर थिकनेस, जब हमारी बाउंड्री लेयर थिकनेस के लिए y इज इक्वल टू डेल्टा, वहां पर हमारा डेल u ओवर डेल y क्या हो गया, 0, क्योंकि इस पॉइंट पे हमारी वेलोसिटी प्रोफाइल का स्लोप क्या है, 0 है. वेलोसिटी प्रोफाइल का स्लोप इज मैक्सिमम एट y इज इक्वल्स टू 0. ओके, so we wrote down that at y is equals to delta, del u over del y is equals to 0. At y is equals to 0, del square u upon del y square is equals to 0. Therefore at any point, if we write at any point del u over del y is actually a function of y. Del u over del y, that is velocity gradient. This is called as velocity gradient. Velocity gradient is actually a function of y, where delta is equals to 4.64 x upon under root re x. Please remember this formula, that delta is the hydrodynamic boundary layer thickness and this is equals to 4.64 x upon under root re x. ठीक है, re x, और re x को फिर हम लोग क्या लिख सकते हैं, re x को हम लोग लिख सकते हैं v infinity x अपॉन अंडर रूट v infinity x अपॉन न्यू. तो यहाँ से एक्चुअली हमें पता चलेगा कि डेल्टा इज प्रोपोर्शनल टू x टू द पावर 1/2. प्लीज रिमेंबर कि x के बढ़ने से जैसे जैसे x हमारा बढ़ता जाएगा थिकनेस भी हमारी क्या होती जाएगी, बढ़ती जाएगी. यही हमने ऑब्टेन किया है यहाँ से, that hydrodynamic boundary layer thickness is directly proportional to x to the power 2. and we will also observe, अब क्योंकि यहाँ डिनोमिनेटर में न्यू है तो जब आप ये चीज यहाँ रिप्लेस करेंगे तो आपका न्यू ऊपर चला जाएगा, तो वही आ जाएगा डेल्टा इज ऑल्सो डायरेक्टली प्रोपोर्शनल टू अंडर रूट न्यू. तो जैसे जैसे काइनेमैटिक विस्कोसिटी बढ़ेगी ये आपका बाउंड्री लेयर थिकनेस बढ़ता जाएगा. मतलब अगर आप वाटर की जगह आप हनी ले लो तो उसमें बाउंड्री लेयर थिकनेस ज्यादा होगी, क्योंकि उसके केस में आपकी विस्कोसिटी ज्यादा हो रही है. तो जितनी ज्यादा विस्कोसिटी उतनी ज्यादा थिकनेस ऑफ द बाउंड्री लेयर हो जाता है. ओके, अगर टाउ की बात करें, टाउ ऑफ द वॉल, टाउ वॉल मतलब वॉल शियर स्ट्रेस, जो यहाँ इसके वॉल पर जो शियर स्ट्रेस लगेगा दैट विल बी इनवर्सली प्रोपोर्शनल टू 1 अपॉन अंडर रूट एक्स. दैट विल बी इनवर्सली प्रोपोर्शनल टू 1 अपॉन अंडर रूट एक्स. तो जैसे जैसे एक्स बढ़ता जाएगा आपका टाउ क्या होता जाएगा, कम होता जाएगा. तो अगर हम एक छोटा सा ग्राफ बनाए बिटवीन टाउ वॉल एंड द शियर स्ट्रेस के बीच में, तो हमारा क्या ग्राफ आ जाएगा, टाउ और एक्स का ग्राफ हमारा ये आ जाएगा. सॉरी, ये जॉइन नहीं होगा, ये ग्राफ आ जाएगा हमारा, क्योंकि इनवर्स प्रोपोर्शन ग्राफ्स हमेशा कर्व्स आते हैं, हाइपरबोलास आते हैं.